Now, we are going to perform the visual inspection of the data. Typically, after a night with Mezcal, we don't end up like that cat, but we end up with quite a few memories. The images used for calibration that we would return to you would be derived from a collection of 10 to 20 bias images, as indicated by the term bias in the English language. And in Spanish we say vías. There are 10 to 20 lanes per night. They would also be what is the most slit image that I displayed to them just a moment ago. Image was slit from every angle of position that was observed, and then of course we would wonder what would become of our ghosts if they were to exist. In general, my typical approach and recommendation is to carefully observe the same spectrum 3 times using an identical configuration for accurate and reliable results. With that, it would enable us to combine them in order to remove cosmic rays in the most natural way possible. This is using a combination that does the median method. That is, it compares 3 images, pixel by pixel, and in those where the median method removes the largest and smallest and keeps the middle one. If by any chance a cosmic object fell into one of them, the cosmic object will be the highest point. Either of the 2 you'd take would be good, so take the one in the middle. An amazing cosmic cleaning. However, we increased the exposure time by a factor of 3. There are others. Other more modern methods can also help remove cosmic rays. Or, for example, when time is running out and there is bad weather and we have little time left to observe, we only observe a slit. So let's use other methods to remove cosmic rays. And the other data sets we would have are the comparison arcs of Torre Argon. There would also be one for each exposure angle. So we have rods, image masses lit, spectra, and comparison arcs. These would be the 4 types of data that we would obtain and download from the telescope. Here we can observe what a bias appears like. It is an exhibition that takes no time. It is only the bias of the load that all pixels have so that we do not have any problems when reducing. And generally, we calculate the averages of 10 to 20 paths in order to subtract. It is a load pedestal that we are planning to subtract from our images. Here we see, for example, that in this case this detector had a pedestal of around 1180. So that would be roughly around the load, give or take a bit, more or less, approximately speaking, if you will. 1000 acts of 65K, well, they're V-few, but removing them practically puts it at 0. These are the top images I mentioned. Here, it's fascinating to see that due to its brightness, we can observe ghostly structures like the one above on the left. These structures are reflections produced by the instrument itself, but they are well documented in the manuals and Professor Mihon's articles, confirming their validity. With that, and they don't harm us. Simply, you have to know how to recognize the ones that exist. This is one more level that tells us perfectly well where the slit is located. This would be a spectrum of a slit. Notice how we have a lot of cosmic rays. All those little dots are cosmic rays. Notice that the emission of the nebula, in this case the one in the middle, is hydrogen H alpha, and the 2 on the sides are nitrogen 2. So, that's just the emission of the nebula. What are stripes? Vertical stripes are lines from the sky. The sky was bright on that night, and the horizontal stripes is a single dot emitting in all colors, which are actually stars. So, in that place we can identify the locations of the stars and the skyline. We shouldn't remove the stars. That's how they are, that's how it is. But we could remove the skylines as part of the reduction to make the spectrum cleaner. Here we have another spectrum. Observe how there are cosmic ones that are almost grazing, and instead of dots, they appear as little lines, but they are cosmic. We also have a shine over there, at the top right. it appears that there is another shine, resembling a ghostly reflection. See how on one side there is an H-alpha line, we have a fainter line, located in the most intense part, and that is the helium 6560 line. Then it is like a high spectrum. Here we have oxygen 3, and you can see that there is also a small emission here next to oxygen 3. This also seems to be a helium line. And well, there we also have a rather energetic object. Alright, how is the comparison arc? Remember, the comparison arc is a spectrogram that we extract from Thor and Argon's lamp. So, there we have a lot of lines. This is the case of oxygen, for example. And we have a table in the observatory, or we have some images, some figures inside the observatory that already identify which are the active spectral lines. And then, when we make a cut of our spectrum, we can compare it with what already exists in the observatory. And that is what will help us in the calibration process of the wave object. So information is important. If we don't have it at our disposal, there are websites where they tell us what it is like. For example, a tone-argon lamp in a certain spectral range. And from there we obtain the necessary numbers for calibration. Well, up to here we concluded with what I call the first session of the high dispersion spectroscopic data reduction and analysis process of planetary nebulae with the Mezcal spectrograph. I trust all the information has been clear. If you have any questions, please get in touch with me, my group, and we can somehow attempt to explain better or further clarify some of the aspects that interest you. Thank you very much for your attention. See you in the second session.